In this lecture, we are going to talk about inductors. For inductors, we have a special model, which is different from the model for capacitors. Here's a coil of the inductor. Here's the voltage. V is a constant voltage, and we close the switch at T0. So there will be a voltage being applied to the inductor, which is exactly V because it's the same terminal. And there will be a current being created or generated inside the inductor. Is actually converting the electrical energy into a magnetic field energy and being stored in the inductor. So the current is flowing inside into the inductor. And VL, which is exactly V, because it's directly being applied to the two terminals of the inductor. So VL equals to L dit over dt. So that's a fundamental model to describe the behavior of the inductor. Keep in mind, because this is constant, so this part is also constant. That's important. And there are several examples to look at the details of the behavior of the inductor. For example, first, let's discharge an inductor using a resistor. So here's the inductor, originally has a current flow inside the inductor. It must from a different circuit, right? Here you have a voltage or something to charge up the inductor previously, but at some point, here's a switch, I just open the switch, so the current will be not being supplied to the inductor anymore. But I'm gonna close the switch over here at T0 at some point. On the other side, it's another circuit. So I'm going to discharge it, whatever being stored in here previously, to the resistor. So initially, there's an I init flowing inside the inductor, but because it's going inside, so it's a positive current. Otherwise, it's going to be negative. I remember that. So the I init is positive, but whatever is going to flow out from the inductor will be negative. So when you are listing the equation here, you need to know that IT, because there will be a IT, it's a current in terms of T, it's going to change because R is dissipating the heat and converting the electrical current into heat. So actually this is decreasing. So IL T equals to I init something, right? We don't know yet. So let's try to derive it. So at least we know ILT times R, which is the voltage across this resistor, equals to whatever is going to be generated, which is actually here, right? So this is negative L DILT dt. So here's the equation we can list. And now let's calculate ILT. So what is ILT? Let's move everything to here. So we're getting minus R over L and dt equals to 1 over ILT DILT. And if we integrate both sides, we are having 0 to t, and this is from I init, the initial current, to ILT. Okay, then we are getting minus RL times T equals to, here's very simple, it's just do a natural log of ILT minus natural log of I init, which is also natural log of ILT over I init. All right, and then do an exponential conversion on the two sides. So you're getting e to the power of negative R over L, T equals to ILT over I init, which is also ILT equals to I init times what? Times this part, which is E minus T over L over R. Just want to keep it the same format as the capacitors equation we just got in the previous lecture. So now we know how to discharge an inductor and how what that looks like. So it just follows a pretty similar methodology like what you used for the capacitors for the inductor, and you will be able to find out the state of the inductor at any time point, right? So that's what the first example I would like you guys to take a look. And now we are going to see some examples. For example one, I get a voltage and a switch and an inductor. So this looks like an RC circuit, but we don't have a cap. Instead, we have an L, which is an inductor. At T0, we're going to close the switch, and initial voltage is V. And here's the grounding. We know that after close it, definitely there will be a current flow inside the inductor, which is IT, which is called IT. So the question here is, what is IT? So just write down the equation or the function for I in terms of T. So what is IT? We just need a expression for IT. So definitely KVL, right? Because this is a closed loop, and we can definitely list the equation here. V equals to definitely IT times R. That's the voltage drop across the resistor, plus the voltage created over this inductor, which is actually L d IT dt. I mean, if we keep writing L over here, then just let's just write it. Um, and then we want to integrate this equation to find out ILT. In that case, we need to move things around to make it work. So first of all, we need to move this to the left, so we have this one isolated from anything else. So it's going to be V minus ILT times R equals to L DILT over dt. And then we want L over here and move T over here as well. So it looks like 1 over L dt equals to 1 over V minus ILT R times DILT. Okay, so this is what we have now, and let's integrate both sides. So we are getting integrate 1 over L dt from 0 to t. On the left side, we have there was no current in the very beginning, so it's going to be I0 being integrated to ILT. And here is V minus ILT times R and DILT. Okay. Next, because this is a little bit hard to integrate, so we have to convert it slightly to something else. So this is actually because the goal is to make this part to be exactly the same as this part, and as well here, this variable should be this thing. So if you want to do that, let's convert this part first. So this will be, I don't have enough space over there, so let's just keep writing over here. I have to have V minus ILT times R here. So in order to get this, I have to time minus 1 over R here in the front to cancel this part, right? The minus sign and R eventually. And in that case, this is exactly this part, so which is great. So we can directly use a natural log for the integration purpose. And since we have changed this thing, so the integration limit has to be changed as well. And because initially it's ILT and now it's times R and minus and plus V. So it's actually just V because it just plugging ILT into here using 0, put it here. So 0 times R is 0, and then only V is left. So here it's the same because ILT is the same as ILT. Directly write down this, and then it becomes either just minus 1 over R times natural log of V minus so this thing minus natural log of V, which is minus 1 over R times natural log V minus ILT times R over V. And here is nothing but T over R, T over L. And we can move this part to here, so we're getting minus R over LT equals to whatever here. And then this one can be converted to this. And which is also this. So ILT will be V over R times 1 minus L over R, which is a constant in the LR circuit instead of RC in the RC circuit. All right, so this may be a little bit confusing for you if you haven't done this in the past. So I recommend you, do not look at the notes and just do it by yourself. If you find out this is really new to you, it's really not that difficult. So after that, we got the very last example for the inductors. I'm going to show you which is LR circuit time delay. Because all the nonlinear circuits is going to cause time delays in the circuit, like we just did for the capacitors. The inductor will give you the same time delay, but we have to calculate it, see what that looks like if we are using inductor instead of capacitor in the circuit. So let's see an example. So now the capacitor is in front of the resistor in the LR circuit. It's slightly different from the RC circuit. And I forgot the switch, so we close the switch at t equals to 0. And the R is 1 millihenry. So keep in mind the Henry is a unit for inductors. And that's a current, we call it IT. And then that's a resistor, which is 100 ohms. And here's a VL. So we just want to find out the time delay for this kind of LR circuit. Use KVL still. So RIT plus whatever flowing. So RIT is the voltage here, right? And you plus whatever being generated by the inductor, which is L DIT dt, of course, and equals to V in. And let's try to move it around, try to integrate it, of course, right? So we can move this to the right side. So we are getting, move everything to the left. Let's just make it look nicer. So it's going to be V in minus RIT equals to L DIT dt. And then move L to the left, move dt to the left. So we're getting this. And it's going to be 1 over V in minus RIT. So you can see that this format looks very similar to whatever we just did in the last example. Okay? And after this, we should integrate both sides. And here is from 0 to IT, right? And then we are going to get T over L equals to, still we have to convert it into something. So we convert it into V in minus RIT, for example. So here will be V in left over here, and here's V in minus RIT. and then 1 over V in minus RIT, and derivative of V in minus RIT. Okay, I'm skipping one step. Just if you don't know how I get from here to here, just look at the last example. And there are many other videos I did it slightly slower in the regular lectures, so you can go back there. I can send you some links, probably somewhere around this video's link. You can refer to that one as well. So this one equals to natural log of V in minus RIT over V in, which is also no, we just directly do it here because you cannot forget this part. So I'm going to move this one to here. I'm getting this equals to this. Then L over R, which is time constant, equals to V in minus RIT over V in, which is also 1 minus RIT. So IT definitely equals to, you have to forget this part. So it will be V in over R times 1 minus L over R, right, which is a time constant for the LR circuit. So that is literally the LR circuit's equation to describe IT. Is pretty similar to whatever we got in the last example. So if you want to look at time delay, which is the V out compared to V in, you have to convert the current into voltage, which is understandable because IT is current flows through this resistor. If you want to get V out, it's just simply times R, right? So IT times R will be V out. So let's do that. So I'm getting V out equals to IT times R, right? Which is pretty simple. And this equals to what? Because IT is this part, so just R times this guy, which is V in, 1 minus E minus T over L over R. So now it looks similar because if you have a step function, you know that there will be a time delay, and 50%, 50%, so this time period will be TD, okay? So in that case, 50% will be 50% of V in, so you are having 1/2 of V in equals to V in 1 minus, so now this is the TD over here, so L over R, cancel, cancel, so you know that this part equals to actually 0.5. Then L over R will be, no L over R, I'm sorry, so TD will be minus 0.7 L over R. Okay. In a similar format, but different values because you have L instead of C over here, and L is right now on the top, R is at the bottom, and it's actually 0.7 L over R will be the time delay if you are not looking at the negative sign, which is telling you that's the time delay is behind the original time. And so whenever you see a LR circuit like that, so you know that VL will have a 0.7 times L over R time delay compared to V in. That's time delay in LR circuit. All right, so that's whatever I want to cover today in this lecture, and I'm going to see you in the next video.